Section 7 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Edward Labonte. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy, Chapter 6, The Solar System, Planetary Distances. To the ancients, as well as to the moderns, the sun and the moon appeared not only the largest, but the most important of all the celestial bodies. With the sun and moon, 5 other conspicuous spheres eventually were linked, spheres distinguished by reason of their regular motions. These orbs, Mercury, Venus, Mars, Jupiter, and Saturn, were named planets or wanderers, to distinguish them from the fixed stars. Venus, familiar as the evening star or the morning star, was discovered, it is claimed, by Pythagoras in the 6th century BC, but even in the poems of Homer there are references to both stars without any indication of their identity. Jupiter, Venus, Mars, and Saturn ranking with the brightest of the stars, and Mercury occasionally seen near the horizon just after sunset or before sunrise. All were known to the ancients. A study of their movements naturally led to the obvious conclusion that all these moving stars or planets were related in some way, and that the motion of one was more or less dependent on the motions of the others. Hence it may be asserted that the ancient history of astronomy begins with the system of planets that revolve around the sun. What is the nature of these planets? Obviously, they are not all alike in size or distance. Even to the naked eye, their appearance seems to reveal conditions that need explanation. Early observation and study revealed the fact that the planets occupied a section of the heavens where there were no so-called fixed stars. But later observation also revealed that associated with the planets are a number of smaller bodies of much the same nature, known as planetoids or asteroids, which, with a single exception, occupy the zone of the heavens between Mars and Jupiter. Lastly, there are a large number of temporary visitors to this solar system, known as the comets. They plunge in from space, sweep around the sun, and drift away by various paths or orbits, most of them never to return. Planets, satellites, planetoids, and comets comprise the solar system. Vast and marvelously complete as that system is, it must be admitted that it is but a part of the great universe. It may be, as there is some reason to suppose, that this solar system is but one of many similar systems scattered throughout the universe, and that each of these, including that in which the Earth is situate, is in turn wheeling about some central orb inexpressibly distant. The solar system to which the Earth belongs is merely a type and not a unique example of planetary order. The intellectual rise in astronomy is nowhere more clearly revealed than in the history of man's conception of the solar system. Perhaps the first inquiry that must have flashed across the mind of a thinking Chaldean or Greek concerned itself with the distances of the heavenly bodies. How far away are the planets? How is their distance measured? The second question concerned itself with their motions. Whither do they drift and why? Around these questions cluster a group of vague guesses, fruitless speculations and poetic fancies, from which at last a scientific method was evolved for measuring planetary distances and accounting for planetary movements. It was not until comparatively late in astronomical history that means were devised for ascertaining the physical condition of each planet. The distances of the planets, small as they seem in comparison with sidereal measurements, are felt to be immense. Using only round numbers, which are sufficiently accurate for the present purpose, the planet Neptune, the outermost known member of our system, is 2,800,000,000 miles from the Sun. In a cord 28 feet long, each single foot will represent 100 million miles. On such a scale, a map of the United States could not be seen without the aid of a microscope. Suppose a bead were placed at each end of this line, one representing the Sun, the other Neptune. Between the two, other beads will represent the other planets. One nearly 4 inches from that representing the Sun will be Mercury, another at about 7 inches, Venus, a third at 11 inches, the Earth, a fourth at 17 inches, Mars, a fifth at about 5 feet, Jupiter, a sixth at 9 feet, Saturn, a seventh at 18 feet, Uranus, and an eighth, Neptune, at the end. The mean distances of the planets from the Sun are as follows: Mercury, 36 million miles; Venus, 67,200,000 miles; Earth, 92,900,000 miles; Mars, 141,500,000 miles; Jupiter, 483,300,000 miles; Saturn, 886 million miles; Uranus, 1,781,900,000 miles; Neptune, 2,791,600,000 miles. Attempts to measure some of these distances approximately are found in early times. The idea that some of the planets must be nearer the Earth than others must have been suggested by eclipses and occultations, in other words, passage of the Moon over the Sun and over a planet or fixed star. No direct means being available for determining the distance, rapidity of motion anciently was employed as a test of probable nearness. The stars being seen above, it was but natural to think of the most distant celestial bodies as the highest, and accordingly Saturn, Jupiter, and Mars, being beyond the Sun, were called superior planets, as distinguished from the two inferior planets, Venus and Mercury. Uranus and Neptune are modern additions to the solar system and could not have been included in the hypothesis. Aristotle, 384 to 322 BC, for example, arrived at the conclusion that the planets are farther off than the Sun and Moon as the result of an occultation of Mars by the Moon, and as the result of similar observations made in the case of other planets by the Egyptians and Babylonians. Ptolemy, 2nd century A.D., although far more original and daring in his astronomical conceptions than Aristotle, was able to add but little toward a solution of the problem. He expressly states that he had no means of estimating numerically the distances of the planets, or even of knowing the order of the distance of the several planets. He followed tradition in conjecturally accepting rapidity of motion as a test of nearness, and placed Mars, Jupiter, Saturn, which performed the circuit of the celestial sphere in about 2, 12, and 29 years respectively, beyond the Sun in that order, as Venus and Mercury accompany the Sun and may therefore be regarded as on the average performing their revolutions in a year. The test, to some extent, failed in their case, but Ptolemy again accepted the opinion of the ancient mathematicians, probably the Chaldeans, that Mercury and Venus lie between the Sun and Moon, Mercury being the nearer to the Earth. Copernicus gave the first glimpse of the truth. To quote Berry in his Short History of Astronomy, quote, "From the fact that Venus and Mercury were never seen very far from the Sun, it could be inferred that their paths were nearer to the Sun than that of the Earth, Mercury being the nearer to the Sun of the two, because never seen so far from it in the sky as Venus. The other three planets being seen at times in a direction opposite to that of the Sun must necessarily revolve round the Sun in orbits larger than that of the Earth, a view confirmed by the fact that they were brightest when opposite the Sun, in which positions they would be nearest to us. The order of their respective distances from the Sun could be at once inferred from the disturbing effects produced on their apparent motions by the motion of the Earth. Saturn, being least affected, must on the whole be farthest from the Earth, Jupiter next, and Mars next. The Earth thus became one of 6 planets revolving round the Sun. the order of distance, Mercury, Venus, Earth, Mars, Jupiter, Saturn, being also in accordance with the rates of motion round the Sun, Mercury performing its revolution most rapidly, in about 88 days, Saturn most slowly, in about 30 years." Unquote. It was not until John Kepler, 1571 to 1630, published his Epitome of the Copernican Astronomy, his Harmony of the World, and a treatise on comets, that astronomers were given a definite formula which enabled them to determine planetary distances with any exactitude. Kepler's speculative and mystic temperament led him constantly to search for relations between the various numerical quantities occurring in the solar system. By a happy inspiration, he tried to discover a relation between the sizes of the orbits of the various planets and their times of revolution round the Sun. After a number of unsuccessful attempts, he discovered a simple and important relation commonly known as Kepler's third law. Quote, "The squares of the times of revolution of any two planets, including the Earth, about the Sun are proportional to the cubes of their mean distances from the Sun." Unquote. In other words, given the periods, there is need only to find the interval between any two of them in order to infer at once the distance separating them all from one another and from the Sun. Here was the plan. What was next to be discovered was the scale upon which the plan was to be drawn. There must be first a trustworthy measure of the distance of a single planet from the Sun, the Earth for example, and the problem would be solved. How is this measure to be obtained? Sir Robert Ball, in his Story of the Heavens, gives this simple example for partial explanation. Quote, "Stand near a window where you can look at buildings, or at any distant object. Place on the glass a thin strip of paper vertically in the middle of one of the panes. Close the right eye and note with the left eye the position of the strip of paper relatively to the objects in the background. Then, while still remaining in the same position, close the left eye and again observe the position of the strip of paper with the right eye. You will find that the position of the paper on the background has changed. Move closer to the window and repeat the observation, and you find that the apparent displacement of the strip increases. Move away from the window and the displacement decreases. Move to the other side of the room, the displacement is much less, though probably still visible. We thus see that the change in the apparent place of the strip of paper as viewed with the right eye or the left eye varies in amount as the distance changes. But it varies in the opposite way to the distance, for as either becomes greater, the other becomes less. We can thus associate with each particular distance a corresponding particular displacement. From this, it will be easy to infer that if we have the means of measuring the amount of displacement, then we have the means of calculating the distance from the observer to the window. It is this principle, applied on a gigantic scale, which enables us to measure the distances of the heavenly bodies. Look, for instance, at the planet Venus. Let this correspond to the strip of paper, and let the Sun, on which Venus is seen in the act of transit, be the background. Instead of the two eyes of the observer, we now place two observatories in distant regions of the Earth. We look at Venus from one observatory. We also look at it from the other. We measure the amount of displacement, and from that we calculate the distance of the planet. All depends then on the means which we have of measuring the displacement of Venus as viewed from the two different stations." Unquote. Two observers standing upon the Earth must be some thousands of miles apart in order to see the position of the Moon altered with regard to the starry background to obtain the necessary data upon which to ground their calculations. The change of position thus offered by one side of the Earth's surface at a time is not sufficient, however, to displace any but the nearest celestial bodies. When there is occasion to go farther afield, a greater change of place must be sought. This can be obtained as a consequence of the Earth's movement around the Sun. Observations taken several days apart will show the effect of the Earth's change of place during the interval upon the positions of the other bodies in our system. But when the depths of space beyond are to be sounded, and an effort is made to reach out for the purpose of measuring the distance of the nearest star, the utmost change of place is necessitated. This results from the long journey of many millions of miles which the Earth performs around the Sun during the course of each year. Still, even this last change of place, great as it seems in comparison with terrestrial measurements, is insufficient to show anything more than the tiniest displacements in a paltry 43 out of the entire host of stars. It is thus readily realized with what an enormous disadvantage the ancients coped. The measuring instruments at their command were utterly inadequate to detect such small displacements. It was reserved for the telescope to reveal them, and even then it required the great telescopes of recent times to show the slight changes in the position of the nearer stars, which were caused by the Earth's being at one time at one end of its orbit and some 6 months later at the other end, stations separated by a gulf of about 186 million miles. It was from an opposition of Mars observed in 1672 by John Richter, unknown date of birth to 1696, at Cayenne in concert with Giovanni Domenici Cassini at Paris, that the first scientific estimate of the Sun's distance was derived. The Sun appeared to be nearly 87 million miles away. John Flamsteed, 1646 to 1720, the first Astronomer Royal of England, deduced 81,700,000 from his independent observations of the same occurrence. John Piccard's 1620 to 1682 later result was just one half Flamsteed's, 41 million. Philippe de la Hire thought that the Earth must be separated from the Sun by at least 136 million miles. The transits of Venus in 1761 and 1769 were employed after other attempts had been made to measure the Sun's distance. The transit of 1769 is of particular interest, not only for a fairly good determination of the Sun's distance, but also for the reason that the celebrated Captain Cook was commissioned to sail to Otaheite for the purpose of witnessing the transit of Venus. At Otaheite on June 3rd, the phenomenon was carefully observed and measured. Simultaneously with these observations, others were obtained in Europe and elsewhere. From a combination of all the observations, an approximate knowledge of the Sun's distance was gained. The most complete discussion of these observations did not, however, take place for some time. It was not until the year 1824 that the illustrious Johann Franz Encke computed the distance of the Sun and gave as the definite result 95 million miles. Later, Urbain Jean-Joseph Leverrier, 1870, reduced the estimate to 91,320,000 miles, which held good until Professor Simon Newcomb in 1882 gave the figure 92,475,000 miles. In 1900, nearly all the observatories of the world, under the direction of Maurice Levy of the French Academy of Science, began a new computation which will lead to more exact results. The old problem of measuring a planet's distance from the Sun is not yet completely solved. If Sir David Gill's plan of basing a new set of calculations on the opposition of Eros in 1931 is carried into execution, the Sun's distance will be ascertained to within 10,000 miles. Present knowledge declares the distance of the planets from the Sun with an error not exceeding 1/50th of 1%. End of section 7.